Okay, let me check if the mic is working. Yeah, perfect. All right. So we'll talk about complex filters. So for the past few days, we learned about IIR filter, FIR filter. So FIR stands for finite impulse response. It's basically a filter with certain number of coefficients, a limited number like 100, 1,000, and so on. IIR filters usually are expressed with a certain expression like x of n equal e to power negative n u of n, for example. So that's an example of an IIR filter. A FIR filter could be represented by having this set of coefficients. Another representation of FIR filters are summation of shifted deltas and so on. Now, for the past, up till now, we've been working with the real valued data with real valued filters, but some applications they require complex valued filters or complex filters. A typical example, actually, that's what I'm working on, are radar images. So radar images are different from, let's say, the standard or optical images. And optical images, so basically you have sunlight, and let's say it hits a certain scene or artificial light scene, and let's say bring any camera and it will capture that scene, and that will be like what we call optical images. Optical images in nature are real valued. Now with radar images, basically what you have like an airplane or a radar device that will send and transmit electromagnetic signals. So that's for, let's say, for example, we have the scene here, a building, some trees, and so on. So basically, let's say the energy source here is not the sun, it's not light, it's just the radio waves or microwave images. And these images, depending on the texture or the nature of the objects on the ground, I'm talking about radar images and remote sensing, so to be precise. So these hit, let's say, microwave signals, when they hit the objects on the ground, they will interact with this object in a different way than optical images. And what will be reflected here will be not just a function of the microwave, so it will be a function of magnitude and phase. So in here we have complex valued data. Processing complex valued data is not as straightforward as dealing with real valued data. Here we have the real part plus J, the imaginary part of the signal. So the topic of this lecture actually is just a simple differentiator, a simple filter with real and imaginary coefficients. And we'll see how the process will happen in complex value domain. So this is just an introduction that complex valued filters actually do exist, and they have applications, not just in remote sensing, but in many other applications. All right, so we'll talk about some general definition here of complex filters, or basically complex valued filters that will be dealing with imaginary and real parts. Simple example of non-recursive filter, and we'll talk a little bit about recursive filter, but most of the work will be on non-recursive filters, basically an FIR filter. Okay, so let me enlarge the scene. All right, so complex digital filters, they are digital filters that are composed of real and imaginary coefficients or complex coefficients. So they are often characterized by their asymmetrical frequency response and complex impulse response, providing that they will always have a real and imaginary part. So usually in the frequency domain, we have, this is what we call symmetrical response. Like this is the center, this is the zero frequency. And so usually in Fourier domain, if you guys remember, whatever I have here, I will have the exact image at the negative frequency. That's a symmetrical property in the frequency domain. Now, with complex valued filters, we don't have that. So they have this asymmetrical nature in frequency response. Okay, so we have what we call the real part, or which is an in-phase part, basically cosine 0, and we have the quadrature part. That's the sine component. So can process both real and complex signals since they have the real and imaginary inputs and outputs. All right, so this is the use case that we have, the non-recursive filter. Basically, it's a filter with a single delay, and you have coefficients. B naught is the coefficients you multiply with the original signal with no shift, and B of 1 will be the magnitude or the gain that you multiply with the shifted version of the signal. So Y of n basically is the addition of B naught x of n plus B1 x of n negative 1. So that's in the real value domain. That's a typical example. Now in their Z domain or the Z transform domain, so B naught is there, you have x of z, and B1 x of z, z to the negative 1. Actually, the transfer function then will be y of z over x of z, and that's going to be the response of that filter. All right. So I believe by now we know how to go from this domain into this domain into this domain. Hopefully you guys remember that, because that's something you probably will face either in the quiz or the midterm. Like if I give you an impulse response and I ask you to draw the block diagram, not the impulse response, the transfer function, and I ask you to draw the block diagram, you should know that this to the negative 1, that's a delay by 1 unit. All right, so in real filters, assuming that values of B0 is 1 and B1 is 1, this is the kind of response that we will get. And notice that the symmetrical nature here at the magnitude, you have something like this over the center. And that is the phase for that filter. Now, when we have complex coefficients, now by complex coefficients or complex values, each term here will consist of real part and imaginary part. That's both for the gain and the signal itself. So even x, you have x real part and x imaginary part. B1 real and B1 imaginary. Same thing for x of n. All right, so my inputs here in this case is x of n, but then I will decompose it into x real of n and x imaginary of n. And I'll treat each one of them as its own single, let's say, input. So it's kind of having a 2-input system. All right, so x of n will be x real plus j xi of n, j to make the number complex, and this is the imaginary part of x, and that's the real part of x. So since I have my inputs real and imaginary, and I have my coefficients also, I have b naught of real, b naught imaginary, I will have also like an output y real of n and yi of n. So basically all the variables that we have seen in this diagram, so this is 1, 2, this one we have real and imaginary, and the output will have real and imaginary. So they become all complex. Now, going back to this original formula here, our substitute for each value, their, let's say, real and imaginary components. So B1, I'll substitute B1, sorry, B naught will be substituted by B naught real plus J B naught imaginary. So that's the first term there. And same thing for B1, B1 real, B1 imaginary. Now my inputs, again, don't have just the real part. So X real of n, J I of n, and I have the shifted version there. And of course, the output will have Y real and Y imaginary with J. Now, what will be like, what the task will be is, if I'm going to give you this general structure and just like represent, find Y I of n and Y real of n, and I'm going to give you the values of B naught equals something, sorry, B naught real, and B naught something, and B1 another thing, but this one will be B naught real plus J B naught imaginary, and this one will be B1 real plus J B1 imaginary. Substitute, and all what you need to do is just to work out the algebra, have the real parts alone, have the imaginary parts alone, and you'll tell me, okay, the real part of y will be this expression, the imaginary part of y will be that other expression. How to represent that in a block diagram will be something like this. Again, as I mentioned, it's as if having two individual inputs for the imaginary part and for the real part, and you need to find the block diagram for each one of them. So you have the x real of n, and that will produce y real of n. Now you will notice that some imaginary components will contribute to the real part, and some real components will contribute to the imaginary part. Like in here, so for example, y real of n, it has this imaginary part of b naught, and so on for the other variables. Now, the typical example, all right, so this one showing an example for complex filter, just to show that now you don't have this symmetrical nature like in real valued filters. In real valued filters, that I was having this symmetrical over the center, but now with complex valued filters with these coefficients, now the gain is not symmetrical over the center. And the phase has this pulse in the phase. It's no longer a linear phase. All right, so what? Okay, probably at the end of the lecture, the example will be there. So basic approaches to complex signals. So we have the n phase, which is the real part, and the quadrature, the imaginary part, can be regarded as low frequency envelope modulation using a complex carrier signal. That's for communication systems. Later on, we'll talk about the modulation and carrier signals. In the frequency domain, this means linear translation of spectrum by step. So that's a narrowband signal with a frequency can be represented as an envelope. Again, yeah, I think more detailed you'll get it in communication systems, but this is some information about real and quadrature components. All right, so some analytical representation here. So the negative frequency component are simply reduced to zero, and a complex signal named analytical is formed. And actually, that's one of the things about complex valued filters. If you remember, in the real valued, we have this like a typical symmetrical Fourier transform here. Now, in complex valued representation, this negative frequency component could be removed, and I'll have only this one. And that's what we call an analytical representation of the filter. So the real signal and its transform are respectively the real and imaginary parts of the analytical signal. That's the standard way, which occupies half of the real signal frequency band, while its real and imaginary components have the same amplitude and 90 degrees phase shift. It just shows you that with the complex filters, you have an advantage that I'm not going to have this part. So it's like in terms of bandwidth, that's a safe bandwidth. You've taken single sideband modulation or not yet? Double sideband suppressed carrier, single sideband. So if you remember, in single sideband, you have this Hilbert transform to create the 90 degrees shift. And single sideband modulator, the block diagram, yeah. Single sideband, like you have this representation, the signal, you have this 90 degrees shift using Hilbert transform to produce the single sideband. Anyways, so analytical signals are, for example, the multiplexed orthogonal frequency division multiplexing and wireless communication systems. That's probably the topic you will take next year. So that's a block diagram for basically the Z transform of this filter, actually. Sorry. Yeah, that's the general expression here. So you will have a Z transform for the delay. Okay. One major challenge for complex filters, actually dealing with complex values, is not straightforward like real numbers. It comes with a computational cost, like more mathematical operations. That's the main disadvantage here. Another disadvantage is you have round of noise due to finite arithmetic operations. Actually, this one everywhere, actually. This round of operations. However, because we have real valued and have double valued, so I'm doing round off in 2 dimensions. So that's why you will have it, let's say, have more impact when compared to real valued filters. The transfer function is more sensitive with coefficients. Now we have the real part and the imaginary parts for the coefficients. So changing one might affect the whole response of the filter, unlike real valued, where you only have 2 real valued coefficients. Some applications, single sideband modulation. So basically in modulation, the traditional one or conventional, you have like two sidebands and the carrier in between. So that's double sideband conventional modulation. Then it was improved by double sideband suppressed carrier, where you don't have to deal with the carrier, because carrier will take about, let's say, probably 60% or 67% of the power. And then the remaining 33 will be for the sidebands. It was solved by removing the carrier, and all the information or all the power will be dedicated for the sidebands. Now, this sideband and this sideband will carry the same amount of information. It was solved by single sideband modulation. So you can either take the upper sideband or lower sideband, doesn't matter. So this is single sideband suppressed carrier. And to achieve this, you need the Hilbert transform, you need complex filters or complex values, etc. Also, modern telecommunications, they rely on complex filters. And dealing with DFT, some operations, when we, let's say, go from time domain to frequency domain and discrete Fourier transform, we usually have complex values or complex numbers. Processing them with complex filters will be more efficient. All right, so to summarize this lecture, that you'll be given an example like this, exactly like this. The only thing I will change are the values of B0 and B1. That's the only thing. So this is the general expression that's going to be there for all signals. I'm talking about this recursive, non-recursive filter for one with a single delay. So calculate YR plus JYI if B0 is given and B1 is given. So the task here is to find YR of n and Y imaginary of n given these coefficients. Now the first step is to do the following. So represent x of n. Okay, since we are dealing with discrete, I'll keep it like this. X real of n plus j x imaginary of n. That's the first part. The other part, I want to represent B0 by B0 I plus j B0, sorry, B0 real plus B0 I. All right. Also, from this one, we can intuitively say that x of n minus 1 equals x real of n minus 1 plus j x of imaginary of n minus 1. All right, so I have all this information. I have this part and I have this other part. Now I realize that B0 is decomposed into the real and imaginary part. So I will write this expression like this. So YR of n. By the way, writing the n is very necessary because we have this coefficients of n minus 1. So you cannot say just x real alone or x imaginary alone. So YR of n plus j y imaginary of n equals. So what is the value of B0? 2 plus j2. 2 plus j2 times x of n. X of n is represented by the real and imaginary part. X real of n plus j x imaginary of n. So that's the first step. Plus B1, it's 1 minus j times x real of n minus 1 plus j x imaginary of n minus 1. So the main task is just to work out the algebra, collect the real values on one side, collect the imaginary values on one side, and you say the real values they equal y r of n, and the imaginary values equal y imaginary of n. So let's do the math here. I'm going to take the question or this expression to the whiteboard. Okay. So by the way, the question is solved in slides. Assalamu alaikum. All right. So this is the question. So I'm gonna rewrite what I did. So I have y real of n plus j y imaginary of n equal 2 plus j2 x real of n plus jx imaginary of n plus b1 1 minus j x real of n minus 1 plus j x imaginary of n minus 1. All right, so let's distribute the multiplication. So I will have 2x real of n plus 2j x real x imaginary of n. So I'm done with the 2 plus 2j 2x real of n. J times j, that's going to be minus 2 xi of n. So this is the result of the first multiplication. Plus, I'm going to do that in the other side at the bottom here. So I have 1 times this value is going to be the same, x real of n minus 1 plus j x imaginary of n minus 1. Then I'll have minus j x real of n minus 1 minus j plus j negative 1 negative, so it's going to be plus x imaginary of n minus 1. So what you need to do is just to gather the real coefficients and the imaginary coefficients. Let's see how it will look like. So basically it's going to be as follows: y real of n equals, I'm going to collect the real parts, 2x real of n. And to avoid confusions, whatever coefficient you take, just dash that one. I have 2j, so I'm going to leave that one. Another j, 2 minus 2xi. It's imaginary of n. Then I have plus x real n minus 1 plus x imaginary of n minus 1. So I took this part and this part. So that's it. That's y real. Now y imaginary, and that's something a lot of students get confused with. So when I say y imaginary, I'm just going to take the complex value only. I'm not going to take the j, because j y of I is going to be 2j x of I. So if I want to have the y imaginary part, I exclude the j. J should not appear in the answer. So in this one here, I have 2xi, 2x imaginary of n plus 2 x real of n plus x imaginary of n minus 1 minus x real of n minus 1. All right. So that's the first part of the solution, because usually I'm going to ask you to draw also the block diagram associated with this system. So if you recall the block diagram, I'll just have a system with only 2 inputs. So I have x real of n as an input. As I mentioned, you treat each one of them as its own individual component. And then for the X real, so there is a part with delay T of S, and here is going to be X real of N minus 1. Similar thing here. Z negative 1. I'm writing both because they both represent delay. I think it's just T, not TS. T, that's a unit delay, or Z negative 1 is a unit delay. And in this one here, that's X imaginary of N minus 1. All right, now I need to multiply with coefficients. So let's finish Y real of N. So first I have X real multiplied by 2. So that's multiplication by 2. Then minus 2 X imaginary. So X imaginary multiplied by negative 2. Plus X real of N minus 1. I'm having this one as it is. Plus X imaginary N minus 1. So you can simply have this adder here. That's X. You can have it like this. So that's the imaginary part. Now, to avoid these kind of intersection, what you usually do is something like this. So I'm gonna remove this intersection, this one and this one. So like one line, you draw it as it is, and this one like this. I'm sure you've done that in circuits. Yeah, like to show that there is no intersection. So just a line jumping. All right, so that's for Y real. Now for Y imaginary of N, we have 2X imaginary. So that's my X imaginary by 2. Okay, I'm gonna draw immediately. So this is my summer or adder. So that's the first component. 2X real of N. I'm having the same there. So I'm taking the signal from here. Or actually like this. Oops. I know it might not be the best looking diagram, but you guys get the idea. X imaginary of N minus 1. So yeah, this one, there's no multiplication by any coefficients. So, and the last part minus X of real of N minus 1. So here, okay, I multiply by negative 1. Okay. And that's it. Now, I'm not about, let's say, the look of your diagram, as long as everything is clear, like where, let's say, a junction like this happens, like jumping over a wire or jumping over a line happens, that's it. That's fine by me. In fact, to me, if you solve this one, that's more than 75% of the mark. This one, just a visual representation of these formulas. Actually, the question is already solved here. So you can confirm 2x minus 2x. See there. Minus 2x plus x real plus x imaginary. Plus x real plus x imaginary. I have 2x, 2x. Okay, plus x imaginary minus x real of N minus 1. Again, make sure this J does not appear in the Y imaginary, because I had this experience. I'm not sure if it was last year or the year before. One student told me, like, this is the imaginary. Where is the J? Because he was looking for this complex value. Again, it's J imaginary. This whole thing, you can multiply it by J. So that's what we do. So you just remove this j and you need to find the imaginary coefficient or the imaginary part of YFM. This is okay. The drawing is not there, but this is the solution. And that's it. This lecture is quite short. And to me, that's one of the easy credit in the midterm. Yeah, sure. Okay, let me just okay. All right. So for the midterm exams up to this point, inshallah, it's going to be next week. Start at 12, right? The exam will start at 12. All right. So that's it for today. So I'll stop the recording. Inshallah. Okay, record. Stop recording.